Okay, so here we're going to take a look at points of calculus with parametric curves. And we're going to start with area under the curve. So the way we want to think of this is okay. All right. So if we recall our formulation of the area under the curve for our variable in x, right? We have our y, which is f of x, right? So this represented the area under the curve. This was a, b, etc. Now the way that changes, now a way to think of it, like I won't go through the exact proof here, but the way to think of something like this, right? If we think of almost like differentials, x prime of t is dx dt, right? So we can think of x prime of t dt to be equal to dx, right? So we can think of our integral. Now I'm going to just change, again, these are just denoting the limits of integration as alpha and beta, right? Just simply to let us know that these are different than the a and b above, right? These are with respect to t, right? So y of t, x prime of t, dt, right? So this will be our formulation for area under the curve for our parameters here, right? So for example, let's say that here I wanted to find the area between the parametric curves x of t equals to t squared minus 2t, y equals square root of t, and the x-axis. All right. Okay. So a couple things that stand out here, since we have a root here, we do have to, that kind of restricts our domain. Right, so right away we see, all right, t has to be greater than or equal to 0. So if we had a grapher, we can try and graph this, or if we didn't, we need to just kind of get an idea of what it looks like, right? So if y squared is equal to t, right, that means that x is going to be t to the fourth minus 2, well, excuse me, y to the fourth minus 2y squared. All right, so we see that it's a polynomial in y, right, a fourth root, and not only that, we could see, doing a little bit of factoring, we could see we have some zeros here, right? The zeros occur double root at 0, and then we have a 0 at positive root 2 and negative root 2. All right, now it opens to the right. All right, so it looks something like this. We have double root at 0, so it just kind of pops back up. It looks something like that. All right. Okay, but since t is greater than 0, y also has to be greater than 0 as well, right? So we can pretty much ignore that part here. All right, so what's being trapped between the curve and the y-axis is this quantity here. All right, and that is if y is equal to the square root of t. Well, that happens when t goes from 0 to 2. Right, so my limits of integration here go from 0 to 2, right? And again, that's in terms of t, right? And then so here now we're looking our formula here, right? So it's y of t, so we'll have root t times the derivative of the x, which is going to be 2t minus 2. All right. Okay, so I think we got the hardest part here, right? Setting up the integral here, and then from here we just solve the integral by distributing the square root. So that gives us 2t to the 3/2 minus 2t to the 1/2. All that is in terms of dt. Integrating here, so we get t is 5/2, so multiply by 2/5. There's already a 2 there, so 4/5. T to the 3/2 multiply by 2/3, so that gives us 4/3 since there's a factor of 4 already, evaluated at 2 and 0. So here we have 4/5 times 2 to the 5/2 minus 4/3 times 2 to the 3/2. All right, 2 to the 5/2, that's what, 32 to the 5th is 32, or 16 times 2, right? So we have a perfect square, so root of 16 is 4, and there's already a 4, so we get 8/5, and there's a root still left in there. And then same thing here, 2 to the 3rd power, all right, that's 8, but 8 is 4 times 2, so root of 4 is 2, there's already a 4 out there. We get 8/3. Oh, excuse me here. That should be 16, right? Because we have the square root of 16, which is 4, and there's already a factor of 4 out there. And root 2. All right, so here we can combine these. Liked common denominator of 15. So 3 times 16, 48, minus 8 times 5 is 40. So we get 8/15, root 5. Not 5, what am I doing? Root 2. Okay? So that would be the area trapped between that curve and the y-axis. Okay. All right. So that's the area between the curve. All right. One other thing we're going to go over here is the length, the arc length in parametric. All right. All right, now if we recall, way back in the beginning of the semester here, we defined the arc length to be this quantity here, right? 1 plus dy dx, oops. Squared, right, dx. Well, now let's see what it would look like in terms of our parametric formulation. So again, just going to rewrite these as alpha, beta, right? Since we just need to make sure that these limits of integration are in terms of t. Now using our parametric representation, we have x prime of t over y prime of t. Excuse me, got that reverse. Right, dy dx we saw in the parametric formulation was y prime of t over x prime of t squared, and then previously the dx we could interpret that as x prime of t dt, right, if we think of it in terms of differentials here. And then we can go further here by rewriting this. I'm going to bring this x prime of t inside the square root, but be careful how you do that. Inside the root, it becomes x prime of t squared dt. All right, and then here we could see distribute this in there. And we see that the arc length can be found using the formula x prime of t squared plus y prime of t squared dt. All right, so that is our formula for arc length using parametric equations. Okay, so from here, let's try an example here. All right, so find the arc length of the circle defined by x equals cosine t, y equals sine of t. So here's our unit circle, right? The parametric equations, right, they define here this orientation here. All right, so essentially what I'm asking for here, or what they're asking for here, is the circumference, which we know, right? 2 pi times the radius here being 1, right? But let's use calculus to kind of prove that. All right. So if we do that, right, and using the formula above, we need the derivative, right? X prime of t would be negative sine of t. Y prime of t would be equal to cosine of t. Right, so in setting up our integral, right, we want to go 1. We don't want to overcount the arc length, right? Even though it can repeat itself if we let t be any real number, right? We just want to go 1 revolution here. So we'll go from 0 to 2 pi square root of the derivative of sine squared plus cosine t squared dt. All right, and then we see here, it's kind of evaluating 0 to 2 pi sine squared t plus cosine squared t dt. Well, I know that that's 1, right? So we get essentially this integral. This is 0 to 2 pi of 1 dt, so that becomes t, evaluated at 2 pi 0, or in other words, 2 pi. Which makes sense, right? Circumference is 2 pi r being 1 in this case here. All right, so we have calculated the arc length here. All right, so now let's do one more example. So for this example, I want to find the exact length of the curve x equals to 1 plus 3t squared, y equals to 4 plus 2t cubed, and this is going to be for t between 0 and 2. Sorry, t between 0 and, excuse me, this is t between 0 and 1. All right, so we'll start again, just applying the formula here. The arc length from 0 to 1. So x prime is 6t, y prime is 6t squared. So we get the square root here of squared. All right, so this becomes 0 to 1, 36t squared, 36t to the 4th. All right, factor out a 36, factor out a t squared. So we get 6t square root of 1 plus t squared dt. All right, here basic integral, or not, shouldn't say basic, a substitution type integral where u is 1 plus t squared. Means that du is 2t dt. So substituting in here, and also the limits. So again, be careful, right? Limits of integration. If I want to do a u sub, limits have to be in u now. So when u is 0, excuse me, when t is 0, right, u is 1. When u is, when t is 1, u is 2. All right, and then here we have 3. Right, so I replace 6t and dt with 3 du. And then here, square root of u. All right, and now we have a straightforward integral involving the power rule. So we get u to the 3/2, so times 2/3 the factor of 3 reduces to 1, and we're left with 2. Evaluated at 2 and 1. This becomes 2 to the 3 halves minus 1 to the 3 halves. All right, and then this becomes here 2 root 2 minus 1, or 4 root 2 minus 2. So that is my arc length here for the given curves.